Good afternoon, everybody. Thanks very much for having me. Happy to be here. I'm just going to test this real quick for a sec. So my name is Andy Prince. I'm here to represent Renix. Renix is a Canadian company that has a steady-state ion exchange platform technology that I'm going to talk more about today. The main reason that everybody is here today is because we share, in one way or another, concerns or interests about water security. It all comes down to that. We all recognize that we don't have a finite supply, or we don't have an infinite supply of fresh, clean water to use for residential or industrial use. And also we don't have an infinite way of disposing the water that we do use. So to be able to be good stewards, protect our ecosystems, and also protect our future prosperity, our current prosperity, we need to come up with new ways that are better, more efficient, more effective at solving some of the problems that industry is creating as we innovate. So I'm going to talk about how Renix is taking part in some of that innovation. Again, ion exchange, I'll talk in a little bit of detail about the basics of that for those that aren't familiar, but what Renix does specifically is develop applications and processes for treating water by ion exchange and steady-state ion exchange. Now, ion exchange is really good for selective removal of soluble compounds from liquids, and specifically aqueous liquids. And from a technical perspective, it doesn't really matter which industry or vertical or segment that you work in, because if it's water, in mining or metals and ingredients in food and beverage, fuel and power, they all use water, and technically water is the same, and it doesn't matter where it comes from. Now, the motivations why different stakeholders and companies and governments want to do separations, so removing one thing from another, may vary by who you are within an organization and from one organization to another. But what we find for our technology is that it is these usual suspects for circled here in green. All of these are soluble in liquid, and we can go after those specifically from water. And these usual suspects of different compounds in water cause different types of problems, whether you're trying to reuse the water back in a process or whether you want to discharge it to get rid of it. So these are all kind of framed, these some of the reasons of value recover, process opportunity, and product opportunity. They're all very optimistic, which we like to be at Renix. But of course, water can be a problem. Contaminated water can be a problem. But it's better if you can frame it as solving a problem, but also creating an opportunity, collecting value, recovering value to create a better business case to support the implementation of a new technology. Now, if you are looking at a water source or water that's been contaminated by some industrial process, there's a long list and a big landscape of different technologies that could be evaluated to address what you're trying to do. And Renix specifically operates in the dissolved management of water purification, and again, specifically in ion exchange. So there's a lot of people here talking about conventional biological treatment, filtration, sedimentation, and that sort of thing, but lots of options, and each technology itself will usually leverage some characteristic about the water to be able to do the separation. Now, about our platform technology and ion exchange, put simply, ion exchange is performed on these small spherical beads. The beads themselves are typically made of polymers, so it's synthetic polymers, but there are natural ion exchange materials. But for this discussion, we'll talk about the synthetic ones. The different polymers, there's a number of different structural polymers that can be selected depending on what is in the water, and how it occurs, how ion exchange occurs. Oh, I can't see that. How ion exchange occurs is that there's functional groups attached to the resin, and those functional groups has a selectivity and an affinity for specific compounds in water. So as the ions are floating around in the water and they come into contact with these beads. A physical adsorption and exchange of what the form of the resin takes place. And now those beads are loaded with that target compound. Now, right now there's dozens of different companies, dozens, maybe hundreds of different companies that prepare and research and develop specific ion exchange resins for different applications. Renix does not do that, but we do use the resins in our platform technology. So what's good about this is that from the customers that we talk to, they don't want to be married to a specific sorbent for their process in case supply chain issues occur, price goes up. They want the freedom to be able to select a different sorbent from a different manufacturer. And as the technology, the nanotechnology and the molecular chemistry develops for these sorbents, we can benefit from that development by housing them in our system. So the way these resins are conventionally used is they're put into packed columns or vessels, and the process water or the feed is put up. In this case, I've drawn it through the bottom, and as the target ions are being captured on the resin within the bed, there's a mass transfer that's taking place, and the mass transfer zone moves its way up through the bed. Once the bed is now exhausted, because there's a finite amount of space on the resin beads and therefore on the column, that column needs to be regenerated. After the column is exhausted, it can no longer treat the water any further and needs to be regenerated. That's usually done with a solution of high ionic strength, a salt, an acid, or a base, and the regeneration takes place typically in the opposite direction. The way this is drawn would be a typical counter current flow, that it's loaded in the opposite direction in which it's regenerated. The chemistry for this type of technology has been used for many decades. It's very effective technologically, but causes a lot of headaches for the operators that are utilizing these systems. They're pressurized. The fact that the mass transfer zone moves from the bottom up or in the top down, it's moving, so it's inconsistent performance, especially with variability of the feed itself. It's inefficient because it operates on a batch, so as soon as it's loaded, it has to be taken offline. The bed itself creates a pressure drop across it, so it consumes a lot of energy to be able to push the liquid in the water through the bed itself. Renix has come up with a platform technology that solves most, if not all, of those problems that I've mentioned. So the way our team has done that is develop this platform that has the adsorption vessel and a desorption vessel where the regeneration takes place. The feed goes in through the bottom, the same as I showed before, and it comes out, has contact with the resin beads, and the target ions are removed and the clean water comes out of the bottom. Now the resin itself physically moves from one vessel to another through what we call our dynamic seals. The dynamic seals are really important for the platform technology because they control the flow of the resin. They control the liquid-liquid interface between the columns because you don't want to mix your regenerant with your feed. And in doing this, when we go upflow, we're able to operate it fluidized. So the entire system itself is fluidized, which makes it a very elegant, robust way to operate ion exchange processes. The fact that it's fluidized allows it to be robust to handle suspended solids, so the likelihood of clogging is virtually eliminated. The mass transfer zone stays constant in the middle, so the chemistry is very stable, very predictable. It happens countercurrent, so a true countercurrent. So the resin itself falls down through the vessel as the feed goes up, which facilitates very efficient mass transfer, so we can load the resin with more of the compounds that we're trying to absorb. So we get different operating profiles when running a fixed bed system, which is here on the far left, where when it's in production, it's running, but as soon as that bed is full, it has to be taken right offline because it can no longer be used. And then it gets regenerated down here. So you get this in production, offline, in production, offline. What engineers and processors have done over the years is implement systems that are continuous ion exchange, and continuous in the sense that they can constantly run the feed. They don't actually have to stop the feed, but each vessel itself still operates at a batch. So you get an overlay of complicated valving and mechanical controls to run that system, but it's quite efficient. With the Renix steady state platform system, we get, again, elegant flow without that stop start, and we get a steady state profile. We have done life cycle analyses with our customers that have have overlaid the performance of equipment against fixed bed systems that were already implemented, and we compared the results after. And every time we do this, for every application and customer we talk with, we find a 50% reduction in OpEx or more. And in this case, we had about a third of the operating costs. For the life cycle analysis, what the company that had performed it for us, they looked into the things on the far right in the legend, the manufacturing and the disposal of the resin, the use of it, the chemicals to regenerate the resin, water, and electricity. As part of the life cycle analysis, it had a lot of environmental considerations. The three different, whether it produces emissions, carbon dioxide, sulfur dioxide, and eutrophication for phosphate, what has to do a lot of the energy, the manufacturing of the resin, disposal of the resin, the vessels, and the total lifespan. And again, we see a typical trend that we use about a quarter or a third of the environmental impact. Another important thing to highlight is just the general performance and profile you get when you're trying to recover a specific compound. When you're operating just the nature of a batch system, you always have to trade off purity or yield. And everybody always wants both, but for batch-based systems, you simply can't have it. You'll optimize it and usually trade one off for the other. But of course, both are important. What we find with our system, just based on the steady state nature of the way the technology is configured, we can simultaneously recover compounds and optimize and maximize yield and purity simultaneously, which is very, very important and impressive, especially when that limits the downstream processing of whatever the output of the system is. The other thing is this new age kind of ion exchange platform goes against the rules of thumb that the conventional users of ion exchange would have come up with in the 80s, 90s, and 2000s, where if you talk to somebody that's been using ion exchange for many years, they'll say around 1 gram per liter is the maximum ion load that a fixed bed ion exchange system can work. We've changed that just because of this cost and operating profile that we get. So we're able to make good, solid use in business cases out of applications as high as 10 grams per liter or 10,000 milligrams per liter. So it really opens up the opportunities of treatment processes. The way we work with our customers is, of course, we have gone through a number of scale-ups over the development of the technology, from a science experiment where it started at the university where the technology was first developed, to a small pilot system that runs at 1 liter per minute. We still have this in our lab, and we'll use it to validate and develop product if we're trying to do a recovery. So if there's a precious metal that we're trying to recover from water, we can produce the material. We have a fully automated demonstration scale system that can load into a shipping container, and we ship that around the world to do site validations, and we'll run for several months to validate the process with our customers. And then above that is essentially commercial implementation, where there's some degree of modularity that once it gets so big, we just have multiple units for redundancy. Which brings us back to how Renix can help contribute to the world's water security. It looks like I came right to the minute, I think. Thank you everyone very much. I appreciate your attention.